Hello again, welcome back to our computer vision series, and today we are going to discuss the paper by Xavier Glorot and Yoshua Bengio from 2010 called Understanding the Difficulty of Training Deep Forward Neural Networks. So I've promised you that we will be discussing papers and reading papers, so here we go. So before we start, I encourage everyone to actually go ahead and just try to read the paper itself. This one is a relatively easy read. Then try to watch the video and look at my explanations, and hopefully it will help to answer some questions. So this is from 2010, right? So this is considered quite early for computer vision. And Xavier Glorot is the guy who's the most known for the Xavier initialization of parameters, which is by now the industry standard in deep learning. And this is the sort of his main paper that actually proposes this initialization. So I'll start with just reading the abstract really quick, and then we'll discuss what is actually happening in the paper itself. Whereas before 2006, it appears that deep multi-layer neural networks were not successfully trained. Since then, several algorithms have been shown to successfully train them, with experimental results showing the superiority of deeper versus less deep architectures. All these experimental results were obtained with new initialization or training mechanisms. Our objective here is to understand better why standard gradient descent from random initialization is doing so poorly with deep neural networks, to better understand these recent relative successes and help design better algorithms in the future. We first observe the influence of the nonlinear activation functions. We find that the logistic sigmoid activation isn't suited for deep networks with random initialization because of its mean value, which can drive especially the top hidden layer into saturation. Surprisingly, we find that saturated units can move out of saturation by themselves, albeit slowly, and explaining the plateaus sometimes seen when training neural networks. We find that a new nonlinearity that saturates less can often be beneficial. Finally, we study how activations and gradients vary across layers and during training, with the idea that training may be more difficult when the singular values of the Jacobian associated with each layer are far from 1. Based on these considerations, we propose a new initialization scheme that brings substantially faster convergence. So yeah, first of all, this is 2010. So right now in 2023, we know that deep linear neural networks pretty much won, that a lot of wonderful achievements were done using just basically dense layers and architectures that come out of linear layers. So transformers, convolutions, recurrent neural networks are mostly built around the actual dense layer, which is linear in nature. More than that, we train these models using the classical approaches that I think are at least a century years old, meaning the gradient descent with slight variations. So we basically take the model and just go ahead and optimize all the weights at once using gradient descent. And we know that it works, and we know how to make it work, partly thanks to this paper. But back then it was not obvious, because in early 2000s, people actually tried doing stuff like that. And it was actually known, so there is a mathematical theorem that proves that making the network deeper is really helpful, meaning that compared to making it wider sort of improves the difficulty of the function that you can approximate polynomially, whereas making the network deeper improves this potential complexity exponentially. So we know that it should be really beneficial to make the network deeper, hence deep learning, by the way. But people actually tried doing that, and they weren't really convinced about the results. because results were not so good, especially compared to other approaches, and they didn't quite know what to make of that. And back then, a lot of discussions revolved around alternative approaches, alternatives to the dense linear layer, like Boltzmann machines, like biologically correct neurons and stuff like that, or alternatives to the optimization method. The one that is discussed in references to this paper is called the layer-wise optimization, where instead of looking at the entire network at once, you sort of fix one layer, look at one layer and fix everything else and only optimize this one layer, and then you repeat the procedure until eventually it sort of converges. So the authors here, they take a different stand. They say that linear dense layers should be enough, provided we have activation functions. The normal gradient descent and the classical optimization approach should be enough. Let's not look wider. Let's not look for alternative approaches. Let's instead focus on this and see what problems it has at the moment and how do we fix them. And that sort of helped solve these problems and, build the deep networks that now give us amazing results. So this is basically one of the foundational papers of deep learning itself. Now let's take a quick look at the dataset that is going to be used in the paper itself. So they basically use two types of datasets. One is called infinite, that is basically being generated with simulated labels. And this is done quite easily. So they generate simple shapes like circles, ellipses, triangles, and then rectangles. They can have different color, different rotation, they can partly overlap. And the task of the network is to distinguish what is happening in this picture. So for this picture with the triangle and rectangle, the network has to say that this picture has triangle and a rectangle. So it's a complex task because of this rotating and overlapping, so the difficulty is good enough. Apart from that, they use the classical datasets used elsewhere in computer vision, so MNIST, low quality, low resolution, handwritten digits. The CFAR, which is again low resolution data set of roughly the same size, about 50K examples of various objects. They have 10 classes. So airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. That's a weird set. Either way. And final one is the sort of artificially miniaturized ImageNet. So ImageNet itself is a giant data set with about 1 million examples and 1,000 classes. They take the low resolution versions of the images and they take only 10 classes to experiment on that. And the actual setup, the actual network architecture is pretty much exactly the same as we did on our first post. So just dense layers, some activation functions in between each layer, gradient descent, everything is exactly how we are used to. Right. And first, we study the activation functions. So here I want to sort of first discuss why do we need activation functions at all? So linear networks without any activation functions would only be able to approximate linear dependency. So if you look at the actual sort of formula for the layer output, we have X as an input, we have A as the parameters, so the output itself is sort of the sum of all the parameters. We can add more layers, which will result in the complex multiplication of these two sums. But the X here, the XG member, it's still just X. So it's just sort of multiplying, taking this particular input X and multiplying it by some parameters. So it's still linear, meaning that if we want to approximate a dependency of the output on the input that is not linear, like x squared or sinus of x, we will not be able to do that with just the linear layers, which is why we need activation functions. So with activation functions, if you sort of layer them in between the actual layers, it is actually proven mathematically by the guy called Bengio back in 1989 that having at least two layers and a sigmoid activation function in between them actually allows you to approximate any function at all. Any smooth, continuous function, you can approximate. Of course, that doesn't say anything about like how hard it will be to actually approximate it, how many parameters will you need, and how will you actually optimize for these parameters. But this is sort of proof of existence, right? Dense layers with sigmoid activations should be enough. And this is how sigmoid actually looks like. So it is non-symmetrical, meaning that it is always above 0. And it's sort of, it goes from 0 to 1, looks like this S shape, hence the sigmoid. And another particularly important thing for what has been discussed in the article is that, like many activation functions, it saturates. So basically, if you go towards the left tail, for example, if you go towards 0, as you approach 0, the line sort of starts to go into a plateau, meaning that the gradient from this activation function is approaching 0 as well. So if you have 0 gradient, you will not be able to optimize what is behind this activation function because nothing is being passed through during the backpropagation stage. So this is not ideal, and we'll see like how exactly that happens in a little bit. And yeah, long story short, sigmoid activation is really bad. Never use sigmoid activation in the middle of the network, at least. So it's usually used as the at the last part before the cross entropy, but using that in the middle of the network is really a bad idea. Apart from this, the authors discuss hyperbolic tangent, which looks about the same, but it is symmetric. So it goes from -1 to 1. And also the soft sine, which also looks similarly. It's also symmetric from -1 to 1, but it has different asymptotics. So it sort of approaches the tail slower, meaning that it will take longer to saturate and the gradient will be non-zero for a longer period of time. Another interesting activation function that is not discussed in the paper, but which is an industry standard right now, is called rectified linear unit. So this is partially linear. So it's always 0 in the left part, and then it is linear. It's a diagonal line afterwards. So the authors discuss two problems. So one problem is the saturation, when you are stuck on this plateau and then the gradient is almost 0, which means that it will be hard for you to even move out of this plateau, and everything behind this activation function in the network will be hard to optimize because the gradient will not flow backwards. Another potential problem is if you are here in the middle, then this activation function basically turns into line, which means that it will not be able to approximate anything useful. And this is one of the reasons why the rectified linear unit is so good nowadays. So it does not saturate, meaning that it goes up to infinity, so it never goes to the 0 gradient here. And here it has most of all of its linearities in this point, around 0. So it works slightly differently, and as proven by a lot of experiments, it works better. But let's take a look at what actually happens to the sigmoid. So here, what is happening is we train the network. We train the network for a lot of time, about 1000 epochs. And then we note what happens to activation values during training. So basically, obviously, on every example, on every image, each layer outputs a lot of numbers, and then these numbers will be different for every image. But we sort of average that out to compute the mean and also the standard deviation. And this is what is plotted here in this graph. So the mean is the solid line here, and the standard deviation is plotted using these bars so that we can understand like how variable it is. And for last layer, layer 4, it's a black line. We can see that right after the start, it goes quickly almost to 0 with almost no variance. And only then, after about 100 of 20k mini batch updates, it sort of starts to go up a little bit and some variance starts. So what is actually happening here is that we have the network that basically is composed of all the dense layers that we have, then the activation functions of the last layer, and then the bias. And since we just initialize all the weights randomly initially, this entire network is really bad at sort of guessing the number, at actually recognizing the pattern. But you also have this bias, and this bias can quickly sort of can be optimized really quickly to predict the basically initial probability of classes, to say that, you know, it's 10% of being 1, it's 10% of being 2, and so on. And so to actually minimize the loss function at this point, it makes sense to just zero out the prediction of the entire network and just use the constant prediction that comes from bias, that is not even dependent on the input image. And this is exactly what is happening here. And the problem, particularly with sigmoid activation, is that in order to drive it down to 0, you have to saturate it. So you're going down this left tail, and the gradient is basically 0 at this point. So just sort of zeroing out the network prediction causes you to stifle the backflow of the gradient, which makes it really hard to train the rest of the layers here, which is unfortunate because they were initialized randomly. And so you need to train them for them to become good, but you have a hard time training them because the gradient doesn't flow back really well. And this is the main problem with the sigmoid activation. And as we can see here, it's much better with the hyperbolic tangent and the soft sine. So this is the similar picture for hyperbolic tangent. So let's take a look at that, right? So at 0, it's just a line. So it has no problems with the gradient. So everything is trained really well here. So we don't see any anomalies on this activation plot here. And same goes for the soft sine. So soft sine is also fine in this 0 point. So the gradient is okay. It flows back really well. So it's not clear if there is any difference. So the asymptotic of the tails is certainly different. But if we take a look at the actual results that we get here, right? So here are the results. So this is the loss function on different data sets. So the less is better. And sigmoid is just much, much worse than anything else. And then hyperbolic tangent, without proper initialization that is discussed later, it's usually a bit worse. But then with proper initialization, it seems to be doing just fine. So this is all thanks to the fact that, you know, we need to zero out the output in some cases, and we don't want to saturate the activation function. So yeah, the sort of quick conclusion out of this is that, you know, never use sigmoid activation. Unfortunately, it is quite popular in the math surrounding machine learning. It's quite popular in all tutorials and lectures and so on. But just don't use it. It'll be helpful for you. Don't use it. Right. Second thing is the actual parameter initialization. So let's take a deeper look into that. By the way, here is another interesting picture that I think is connected to the way sort of gradients saturate. So here is the comparison of cross-entropy loss to mean square error loss with just two layers with two parameters. So it's like the 3D picture. And so cross-entropy is black, and it behaves really well in that it does not saturate. And then the mean squared error, we can see the 4 plateaus here with the extreme values of parameters. So it saturates more than the cross entropy. Good to know. Right, so what is actually happening here? I would advise you again to take a look at the paper and try to follow the math yourself. And here are just my explanations for it. So basically, let's revise the actual backprop algorithm a little bit. So how does it work? We have a neural network that is basically a function of output as dependent on the input. And we want to do the gradient descent. So we want to compute the gradient of the output, the loss function, in respect to parameters. Neural networks can be represented as computational graphs. So here we can say that these red guys are the parameters, then the blue guys are the sort of external inputs. So here, this one is the image itself, and this one is the target, the actual true label for this example. And the orange here is the loss. So basically, this sort of looks like dense layer activation function, dense layer activation function, dense layer activation function, dense layer activation function, then output and loss. And so during the forward pass, we just apply the function, right? So it can be anything. It can be activation function, it can be some dense layer, it can be anything else. We just need to know like the actual function, and it can be a scalar function when you have just one input and one output. It can be a vector function depending on the vector of inputs. So you have many inputs and then many outputs. And a good example of that is just the dense layer that can be written down in the following way. So we have inputs denoted by the index j. We have the outputs denoted by the index I, and then to get the ith output, you just sum over all the inputs with the weights. And this weights is actually the thing that is getting optimized in the network. Then during backprop, basically the origin of the backprop itself is the chain rule from primitive calculus. So you have this complex function y equals f of g of x, then the partial derivative of y with respect to x is then partial derivative of f in respect to g times partial derivative of g in respect to x. So this is a simple formula, and obviously this is just for an example of two functions applied in a row, but you can have more. You can have a long computational graph, and then as you go backwards, you have this sort of multiplication of the derivatives. And in case there are many paths, you have to sum up over all of these possible paths. For example, we can, again, sort of, one of the good things about such representation is that you can focus on one node at a time and just forget about everything else. You can, what you need are two things. What you do during forward prop, how you compute the actual output knowing the inputs, and then how you do the back prop. So knowing the gradients of your outputs, how do you pass these gradients to your inputs, and how do you update your parameters? And the rule here that follows from the chain rule is that if you have the scalar output, you just multiply it by your own derivative and pass it backwards. And then if you have multiple outputs, multiple inputs, instead of the simple derivative here, you would have the Jacobian matrix, which is basically just the matrix of all the possible partial derivatives. And then you would sum over all the outputs that come into your node with their respective gradients. And so, for example, for dense layer, the most popular one in deep learning, the output is just this sum of weights multiplied with the inputs. And the Jacobian is really simple because, taking the partial derivative of linear function is just this weight here. So the matrix of weights is actually the Jacobian as well. But important thing to understand here is like what is actually happening in this sum, right? So I denote nj as the number of inputs to the layer, and then nj plus 1 as the number of outputs, which will be the same as the number of inputs for the next layer. So when we compute the output, we sum over all the inputs. So we have nj inputs. But then when we sort of compute the gradient that we should pass backwards, we sum over all over our outputs, and we have nj plus 1 of them. This is the main difference that becomes really important once you talk about variances. So what will happen to variances, right? So what is variance to begin with? We have data that varies from example to example, and then we initialize our parameters randomly. So we can look at this node. We don't know what is coming from the input. It can be just the input image, input example, input data. It can be just the output of some previous layer. But let's just say that it had some variance in it, right? So it had a variance. And then what will happen to the output variance? Well, we know that the variance is additive. So if to compute output, we sum over nj inputs, the overall, ni inputs, the overall variance will be multiplied by the parameter variance that we have in this layer times this ni, right? So, and since we can have the really, really long computational graph here, each time we go forward, the variance will be multiplied by this factor. So ideally, we want this factor, this ni times parameter variance, to be 1. We want it to be exactly 1, because even if it is 1.01, and you have 10,000 layers, due to a lot of multiplication, your variance will basically explode. Your variance will be equal to thousands and thousands, and your network will do extremely, extremely high predictions, which is not good. The same thing happens if this member here is slightly below 1. So if it is 0.99, again, after 1,000 of layers, the variance will basically drop to 0, and your output of your network will be pretty much constant. And we have this ni here, so basically this multiplication factor depends on the size of the input to this layer. And if you look at the gradients now, when doing the backprop, since here the sum is performed over all the outputs, the actual formula is similar, right? So we take the gradients that we receive from the output layer, we multiply it by parameter variance doing the sum, but now we sum over the size of the next layer, right? And again, we want, since the network can be potentially long, we want this parameter to be roughly equal to 1. Otherwise, now the gradients will either explode or go to 0. So we basically have conflicting requirements, right? If the layers are different, if the actual sizes of this layer and the next one are different, then there is a conflict here. We'll not be able to initialize the parameters in such a way as to satisfy both of these conditions. And so the sort of default thing to do was to initialize parameters like that, which sort of helps with the forward pass, but then you would get vanishing gradients with the backward pass. So basically, there's a conflict there. So the authors propose a compromise where the variance is just 2 divided by the sum of the size of this layer plus the next layer. And because we use uniform distribution, the actual boundaries for uniform distribution will also have this square root of 6 here. So basically there's an extra 3 because of the way variance of the uniform distribution is connected to the boundary. And so this is exactly what is called Xavier initialization. So this is now an industry standard to initialize weights in the long, deep networks, at least. And then they actually study the propagation of gradients. So this plot is about sort of activation values for different modes of initialization. So one was the default one that is not using this condition here, and we can see that it starts to go up for higher layer, and then if you use this Xavier initialization, then activation values are pretty stable for all layers. And here is the same for the gradients. So again, here layer 1 has vanishing gradients. Basically, they are much smaller than gradients of all the other layers. So basically, as you go backwards, you have this multiplication factor that is below 1. And so the further back you go, the less your gradients, and that sort of stifles the optimization for initial layers of the network. And then with the proper initialization, they are roughly equal, which is good. But then again, this is not everything that we can do, right? Because if we have really deep networks with hundreds of layers, it is still going to be unstable, right? So it's a good thing to initialize the network in a proper way. But then, since the factor is multiplicative, right? If it goes slightly off the actual output or the gradient that is being propagated backwards, it will be multiplied by itself 100 times. So it still has some instability in it. So, Xavier initialization is not enough for the network to train well, but it's a nice, good step. It's an industry standard, so it's suggested to always use it when appropriate. So one thing that is a limiting factor here is the fact that they actually don't talk about activation functions. So basically they are saying that, let's imagine that we are stuck here in the linear mode where the gradient is roughly 1. And obviously this is not the case in many cases. So for proper installation, you might want to look at the actual gradient from the activation function as well. But this is the sort of simplified version of it. So this was it. Once again, 2 main conclusions from this paper are: don't use sigmoid activation, and do use Xavier initialization. Thanks everybody, and see you soon.